Hey guys, today we're going to look at buoyancy, and specifically the buoyant force, when we compare a penny and an ice cube that have been dropped in water. Okay, so let's first look at this ice cube. We just plunked it in a glass of water, and when we do that, it's not going to hit the surface and stay at the surface. It's actually going to go a little bit below the surface. That's what we see here. The deepest point that it's going to get before it goes up, we took a snapshot of it. That's what we're seeing. Just because this ice cube is in a glass of water doesn't mean it's exempt from feeling the force of gravity. If we take a look at the center of mass of this ice cube, we'll say it's right there, right where that purple dot is, we know that the gravitational force is going to act straight down. And we're going to call this F sub g. There's also another force that's acting on this ice cube. It's not hard to imagine that once we plunk this ice cube into this glass of water, it's going to reach this level, and at this level it's going to stop for a split second, and then it's going to go up. Despite the gravitational force that's acting downward, there needs to be a force that's causing it to go upward. Well, you probably guessed it based on what this talk is about, so it's the buoyant force. And that's going to be depicted by this arrow, which we're going to call F sub b, the buoyant force. Well, I drew it like this for a reason, with the buoyant force arrow larger than the gravitational force arrow. Why? Because I know, just from experience, that the ice cube is going to go up. And so whatever force is pushing it in that direction must be greater than the force that is pulling it down. But now let's look at the equation. The buoyant force is equal to three variables multiplied together. It's equal to the density of the fluid, rho sub F, times the volume of the fluid displaced, V sub F, times g, gravity. The gravitational force, on the other hand, is equal to mass of the ice cube times gravity. These don't really look that similar, but they are. We need another equation, though, to address how similar these two are. And that's going to be our density equation. Density is equal to m divided by v. Density, rho, is equal to mass, m, divided by volume, v. So if we rearrange this and solve for mass, we get mass is equal to rho times v. If we plug that in now for our mass in our gravitational force equation, we're going to get gravitational force is now equal to density of the object times volume of the object times gravity. Aha! And now, look how similar this looks to our buoyant force equation. If we compare these two, we know because this ice cube is fully submerged that V sub F and V sub O are equal to one another. If you were going to submerge your entire body underneath the water, the volume of water that you are displacing is equal to the volume of your body. Just like this ice cube. However much volume of water that this ice cube is displacing, V sub F, must be equal to the volume of the ice cube, V sub O, because it is fully submerged. So that means the differences between these two forces, F sub b, the buoyant force, and F sub g, the gravitational force, is just the density of the fluid and the density of the object. And this is why everyone says that if you put something that's less dense in a glass of water, it will float. Because the densities here are actually dictating the difference between these two forces, as long as that object is fully submerged. All right, now let's go take a look over at this penny. We got this penny over on the left, and as you can probably guess, this penny's going to sink. But let's take a look at the forces. So finding the center of mass of this penny right in the middle, denoted by that purple dot, we know the gravitational force is acting on this penny downward, F sub g. And we know there's a buoyant force, of course, pointing upwards, F sub b. And again, I drew these arrows to depict that the larger one, F sub g, is greater than the buoyant force, F sub b, because I know this penny sinks. We know F sub b, just like the buoyant force on the ice cube, is equal to density of the fluid times volume of the fluid displaced by the object times gravity. Looking at the gravitational force here, it's the same variables for our ice cube. I'm just going to skip that first step and go right to the density times volume times gravity. And now we have density of the object times volume of the object times gravity. And because, again, this penny is fully submerged, the volume of the fluid displaced is equal to the volume of the object. Gravities are the same. So what's dictating the difference between the buoyant force and the gravitational force? Well, it's the density. The density of the penny is greater than the density of the fluid here being water. And because of this, the gravitational force is greater, and because of this, its net movement is down towards the bottom of this glass. And that's why the penny sinks. In this example, we have 3 balls labeled 1, 2, and 3 at the bottom of a tank of water. What we know about these 3 balls is that they have the same density and that their density is less than the density of water. It might seem odd to you that they're at the bottom of this tank of water because their density is smaller than water and thus they should float, but let's just, for this example, pretend that someone held them at the bottom of this tank of water. And at the second we took this picture, they just let go. So right before they're moving. And the question could be, which is going to reach the surface of this tank of water first? In order to answer this question, we should look at the force diagram for each one of these balls. We know that ball 1 has the same density as ball 2 and ball 3. And off to the corner here, I'll write our density equation. P is equal to m over v. If ball 1 has the same density as ball 2 and ball 3, and its volume is smaller, according to this equation, that means its mass is smaller. And if its mass is smaller, we know its gravitational force, F sub g, is equal to m times g, must be smaller. This also tells us that ball 2, because it has a larger volume than ball 1, has a larger mass because it has the same density. So its gravitational force is a little bit larger. And for the same reasons that ball 2 has a larger gravitational force than ball 1, ball 3 has a larger gravitational force. Again, this is because of the density equation. Because all 3 of them have the same density, the one that has the largest volume must also have the largest mass. And because of the gravitational force equation, the one that has the largest mass must have the largest gravitational force. So now let's check out the buoyant force. The buoyant force equation, I'll write this right above our density equation, is F sub b is equal to the density of the fluid times the volume of the fluid displaced times gravity. Well, let's look at ball 1. Ball 1 does not have a very large volume compared to ball 2 and ball 3, which means the buoyant force should not be as large as it is for ball 2 and ball 3. The buoyant force, let's say, is this large. We know it needs to be larger than the force of gravity because we said the density of ball 1 is less than the density of fluid. And in our last example, we said that if that's the case, we know that the object will rise, just like that ice cube. For ball 2, how is this arrow going to look? Well, this arrow is going to be longer because it's displacing more fluid. Per the buoyant force equation, it's going to have a larger buoyant force. Ball 3 is going to have a larger buoyant force than ball 2, which is going to have a larger buoyant force than ball 1. If we manipulate our gravitational force, we're going to get the force of gravity is equal to the density of the object times the volume of the object times gravity. And here, it's the volume of the objects that is changing. So the differences between the volume is what is causing the difference in the gravitational force. Likewise, the distance in the volume, again, is what's causing the differences in the buoyancy force. So the differences in the gravitational force are exactly the same as the differences in the buoyant force. And so if one has a larger gravitational force, it must also have a larger buoyancy force by the same amount. That is why all 3 of these balls reach the surface at the same time.